The Leibniz theorem is basically a general version of the product rule in differentiation. To find nth order derivative of product of two functions, the Leibniz theorem comes into the play. Before going into the theorem, let's appreciate the beauty of this theorem by looking at first few order derivatives of product of two functions. Suppose we have two functions u and v, and we want to find its first order derivative. See, it would have been nice if the first order derivative of product of u and v is just derivative of u times derivative of v, but it is not that simple. We have product rule in differentiation which says keep first as it is, then multiply that with the first derivative of v, then there is a sum in between, then take first order derivative of u, then keep v alone. This is our product rule in differentiation. This is product rule in differentiation. And to find its second order derivative, we have to differentiate this function. And here we have two terms, and in each term we have product of two functions. So we have to differentiate this one plus differentiate this one. And here we have to apply product rule. Also here we have to apply product rule. For product rule of this one becomes keep first as it is, then derivative of second, derivative of v1 is second order derivative of v, then plus derivative of first one, keep second as it is. So this is the product rule for first term. For second term we have keep first as it is, then derivative of second plus derivative of first, then keep second as it is. Now collect all like terms. We have u v2 plus 2 u1 v1 plus u2 v. Next, for third order derivative, then we have to apply product rule for this one and this one. We have to apply 3 times product. Then we have 6 terms. Then we have to collect all like terms, and it gets messier and messier even for higher order derivatives, for the fourth order, fifth order, and so on. But Leibniz theorem, we have everything done for us already. Put n equals to any number, then you have its nth order derivative of product of two functions. And the terms of this Leibniz theorem are arranged very nicely. Let's look at, see, to find nth order derivative product of u and v, start, in each term we have derivatives of u, and it goes up to nth order derivative, and it starts from 0th order derivative of u. For any function f, we define its 0th order derivative as same function. 0th order derivative means no derivative of that function. That means keep the function as it is. So 0th order derivative of u is u, then its first order derivative, second, and so on up to n. Its derivative gets increased by 1 in each term, and derivative of v starts from its nth order derivative, and it gets reduced by 1 in each term and goes up to 0th order derivative of v. And in each term we have coefficient, and it starts from nc0, nc1, nc2, and goes up to ncn. So its general term looks like ncr, and for r we have derivative of u, rth order derivative of u, and n minus rth order derivative of v. So this is Leibniz theorem. And what is ncr? ncr is n factorial over r factorial times n minus r factorial. And in this video we are not going to prove this theorem. I will just apply this theorem and solve some of the questions. Let's see. First question. We have find the nth derivative of x log x. See, we have product of two functions, one is x and log x, and we want to find its nth order derivative. We will apply Leibniz theorem. So for Leibniz theorem, let us take, let u be the first function x and v be log x. So for Leibniz theorem, we have to find all derivatives of u up to its nth order derivative, and all derivatives of v up to its nth order derivative. So what is first derivative of u? It is 1. Second derivative of u is 0, and third derivative 0, and all other derivatives are 0. What is its first derivative of v? It is 1 over x, which can be written as x to the power minus 1. Second derivative of log x is minus 1 comes out, x to the power minus 2. And what is its third derivative? Minus 1 times minus 2 times x to the power minus 3, power gets reduced by 1 and the power comes out, and this is 1 times 2 times x to the power minus 3. For the moment, let's not multiply all these terms. To find a pattern, just keep it as it is. Let us find another derivative, v4 is 1 times 2 times minus 3 times x to the power minus 4, minus 1 comes out and it is 1 times 2 times 3 x to the power minus 4. So let's observe the pattern for its nth order derivative. See, for its nth order derivative, we have x to the power. For fourth order derivative, we have x to the power minus 4, third x to the power minus 3, second x to the power minus 2. So in each term, we have x to the power some power, and for third it is minus 3, 4 it is minus 4, for n it will be x to the power minus n. And the sign of the derivatives for odd order derivative, for 1 it is positive, for 2 it is negative, 3 positive, 4 negative. So when n is odd it is positive, and when n is even it is negative. So this will be minus 1 to the power n plus 1. When n is odd, n plus 1 is even, and minus 1 to the power even is positive. And for when n is even, n plus 1 is odd, minus 1 to the power odd is negative. So for even we will have negative, and for odd it is positive. And what about other terms? See, in 4 we have 3 times 2 times 1, so it is 3 factorial. For 3 it is 2 factorial. For 2 it is 1 factorial. For 1 it is 0 factorial, which is 1. So for n it is n minus 1 factorial. So here we have derivatives of u and derivatives of v. Let's apply the Leibniz theorem. Apply the Leibniz theorem. Leibniz theorem have u v n equals to nc0 u bn plus nc1 u1 v n minus 1 plus nc2 u2 v n minus 2. See, all these terms are 0 because we have u2 0, u3 0. So all these terms are 0 terms. So we only have 2 terms, and nc0, what is u? U is x. What is vn? Vn is minus 1 to the power n plus 1 n minus 1 factorial x to the power minus n plus nc1. What is u1? u1 is 1. And what is vn minus 1? Put n minus 1 in place of n, because nth order derivative is this one. So in place of n we will put n minus 1. So it becomes minus 1 to the power n minus 1 plus 1, which is n, and n minus 2 factorial, n minus 1 minus 1 x to the power minus n minus 1. So let's simplify. Now we have, what is nc0? nc0 is n factorial over 0 factorial and n minus 0 factorial. What is 0 factorial? 0 factorial is 1. So it is also n factorial, so it is 1. And what is nc1? nc1 is n factorial over 1 factorial times n minus 1 factorial, which is n, because in n factorial we have n times n minus 1 up to 1, and here we have n minus 1 up to 1, and they will be cancelled and we have only n. So this becomes nc0 is 1, so minus 1 to the power n plus 1 x to the power minus n plus 1, and we also have n minus 1 factorial plus this term is n times nc1 is n and minus 1 to the power n minus 2 factorial x to the power minus n. This is also plus 1. So we have, let's take the common terms outside. We have minus 1 to the power n. Here we have n plus 1 times minus 1. We have n times minus 1, so I can take minus 1 to the power n outside, and x to the power minus n plus 1 is common in both of them, and we have n minus 2 factorial in each of the term, because here we have n minus 1 factorial, which is n minus 2 factorial times n minus 1, and so here we are left with only minus 1 plus minus 1 to the power n is already outside, this one is also already there, and also we have, sorry, this is minus 1 times n minus 1, and here we have plus minus 1 already gone, n minus 2 factorial, and we have n. So this becomes minus 1 to the power n x to the power minus n plus 1 n minus 2 factorial, and this is minus n minus minus plus, and here we have plus n, so minus n cancels and we have only 1. So this is our nth order derivative of x log x. Now let's solve this question. Here we have y some function of x and some equation containing higher order derivatives of y, and it starts from n plus 2th order derivative, n plus 1th order derivative, and n. For this type of problem, see, our highest order derivative is n plus 2th order derivative. So first find some equation involving second order derivative. So we have to first find first order derivative, then by some type of differences, either implicit or explicit, find second order derivative of y, then apply the Leibniz theorem. See, let's do that. Here we have y equals to this one. So what is its first order derivative? So we'll apply chain rule, log of something. So outer function is log. So 1 over the inner part, which is x plus 1 plus x square root, then the derivative of inner by the chain rule, and which is derivative of this one 1 plus derivative of this one and derivative of this one. Here we will also apply the chain rule. We have m1 plus x square to the power 1 over 2, sorry, and 1 over 2 comes outside, 1 plus x square to the power 1 over 2 minus 1, which is minus 1 over 2, then derivative of 1 plus x square by the chain rule, which is 2x. Derivative of 1 is 0, derivative of x is x square is 2x. Let's simplify this one. Here we have 1 plus x plus 1 plus x square root, and 2 gets cancelled, 1 plus x square is in the bottom square root, so it will be 1 plus x square root plus x over 1 plus x square root, and this is same as this one, and they are multiplied, so we can cancel them. So we have 1 over 1 plus x square. So this is our first order derivative. Now when there is a square root, it will be better if we square both sides. Now square both sides, so y1 square equals to 1 over 1 plus x square. Now take 1 plus x square to left hand side, we have 1 plus x square y1 square, which is 1. Now differentiate once more to find second order derivative, which is implicit differentiation. Differentiate both the side, differentiate both sides with respect to x. So in left hand side we have product rule, keep first as it is, then derivative of second, which is 2 times y1 by the chain rule 2y1, and derivative of y1. Here we have already first order derivative, so it will be second order derivative. Derivative of y1 is y2, and sorry, here we have one plus in between. Then take the derivative of first, which is 1 plus x square, derivative 1 plus x is 2x, and leave second as it is, and right hand side becomes 0, derivative of 1, which is a constant. See, this 2y1 is here, and here we also have 2y1 square, so we can cancel them. Here we have 0, so it becomes 1 plus x square y2 plus x times y1. Here we have y1 square, we are cancelling only 1 y1. So this is our equation involving second order derivative of y. Now we are going to apply Leibniz theorem to find n plus 2th order derivative. So now apply the Leibniz theorem. Apply the Leibniz theorem. See, To apply Leibniz theorem, we have two terms. We have to find nth order derivative of left hand side and right hand side, and we have to find nth order derivative of this term plus nth order derivative of this one. So we have to apply Leibniz theorem for this one and this one. So let's write nth order derivative, or take nth order derivative of both sides. So nth order derivative this one, which we will apply Leibniz theorem, and Leibniz theorem says this is nc0, keep first as it is. Then nth order derivative of b, this is u, this is b. Nth order derivative, here we have already second order derivative, so nth order derivative will be y n plus 2, and next we have nc1 for 1 first order derivative of 1 plus x square, which is 2x, and n minus 1th order derivative of y2, which is n minus 1 plus 2, this is n plus 1, plus nc2 2. So second order derivative of first one, second order derivative, first derivative of first order derivative, so derivative of 2x, which is 2 times, and n minus 2 third order derivative of y2, which is yn. See, and for next term we have nc3 and third order derivative of this one. This is our second order derivative. For third order derivative we have to take derivative of this one, which is 0. So all other terms are 0 after that. Third order 0, fourth order 0. So rest of the terms are 0. And so this is Leibniz theorem for first term. Now let's apply Leibniz theorem for second one. For second one we have same nc0 and keep first as it is, x, this is u, this is b, and nth order derivative of y1, so n plus 1. We have already taken its first order derivative. Next we have nc1, then first order derivative of this one is 1, and n minus 1th order derivative of this one, n minus 1 plus 1, which is n, then plus, then we have to take second order derivative of this one, x, which is 0, so rest of the terms are 0. And so this is Leibniz theorem for second term, and for right hand side nth order derivative of 0 is 0, first order derivative 0, second 0, and so on. So now let's collect all the like derivatives together. So before that we have to put the values of nc0, nc1, and so on. So what is nc0? We have already found, this is 1, nc1 is n, and what is nc2? This is n factorial over 2 factorial times n minus 2 factorial. In n factorial we have n times n minus 1 times n minus 2, and this goes up to 1. In n minus 2 factorial we have n minus 2 factorial, n minus 2 times n minus 3, and goes up to 1. So here we have n times n minus 1 times n minus 2 factorial. So we can cancel n minus 2 factorial from both sides, from up, and we are left with n times n minus 1, and 2 factorial is 2. So this is nc2. Let's put the values of this one. So nc0 is 1, and this becomes 1 plus x square y n plus 2. nc1 is n, so this is 2x y n plus 1. nc2 is n times n minus 1 by 2, and 2 y1, and this is 1, so x times yn plus 1. nc1 is n, so n yn, which is 0. Now collect the derivatives, like derivatives together. We have n plus 2th derivative, this is only one term, so 1 plus x square, plus for n plus 1th order derivative we have this one and this one, so take n plus 1 yn plus 1 common, and we have 2nx plus x, and for nth order derivative we have this one and this one, and take, then we have n, see 2 gets cancelled, here we have n square minus n, and here we have plus n, which is 0. So this becomes 1 plus x square yn plus 2, plus here we can take x common, so we have 2n plus 1, and this is n square minus n cancels and equals to 0. So let's check. So we have this statement, and this is 1 plus x square yn plus 2 yn plus 1 yn plus 1 and 2n plus 1x 2n plus 1x, and this is n square yn equals to 0. So we are done. So in this Leibniz theorem, we have problems of the type first type, find nth order derivative of product of two functions, or problems of this type where we have some function and we have to prove one equation and we have to find the highest order derivative. We have to see whether it is n plus 2 or n plus 3. Then if it is n plus 3, then we have to go from first order, second order up to third order, and then apply Leibniz theorem. So this is it. For any doubt, please comment in the comment section and let me know if I will make some other video regarding Leibniz theorem, and put your questions in the comment section. Thank you.